In this video, we are going to be doing some diploma-style questions that involve the Bohr's atom. But before we get to that, I have to first go over some more definitions about the Bohr's atom. First, we're going to look at a Lyman jump. Well, a Lyman jump is a quantum jump where the electron jumps down to the first level. So remember, when an electron jumps down, it's going to produce a photon going out. So we could go from any level, as long as it ends in the first level, that's going to be a Lyman jump. Next is a Balmer jump. A Balmer jump is anything where the electron jumps down to the second level, to the second energy level, from any energy level down to the second, and then releasing a photon. Then we have the Passion. Now the Passion is when it jumps down to the third level, and then we have a bracket which is jumping down to the fourth level. These are all definitions that you need to know for your diploma. So let's say we have a question like this. It says, determine the wavelength emitted for the fourth line of the Lyman series. So this question is essentially the same as our question in the last video because it's jumping from the fourth to the first line. But I'm going to show you a different way of doing this. So how we're going to do this one is the only energy level we must memorize is the first energy level for hydrogen. Otherwise they'll give you the other for other atoms. Is going to be my E1 is going to be 13.6 electron volts. Now we want to know what the other levels are. So our formula for that is my energy level for any level is going to be equal to my energy level of 1 divided by n squared. So we want the fourth energy level. So that's going to give me 13.6 electron volts divided by, and we want E4, which is going to be 4 squared, which is going to end up giving me 0.85. So now I know what E1 is, my energy level of the first one, and my energy level of the fourth. Okay, so now we have to figure out what is the difference between E1 and E2, because the difference of the jump is going to be the photon released. So I'm going to go which is equal to, or gets me, 0.85, negative 0.85 minus negative 13.6. And these are both electron volts. Now, once I subtract these, I'm going to get 12.75. But we need this in joules, so I must multiply it by 1.6 times 10 to the negative 19 coulombs. Or, sorry, joules, which is going to end up giving me a total of 2.04 times 10 to the negative 18. Okay, so now we know my change in energy. So now that we know my change in energy, we can figure out what the wavelength is. So this change in energy is going to be the energy that is released with the photon. So that is going to be, my energy is equal to Planck's constant times my frequency. But we know my frequency is equal to the speed of light divided by my wavelength. So I'm going to plug this here in for my frequency. So now I look at this, I'm going to end up getting Planck's constant multiplied by the speed of light divided by my wavelength. So now I must rearrange this formula to find my wavelength, which is lambda. So we get lambda is equal to Planck's constant multiplied by my speed of light divided by my energy. So I'm going to end up getting lambda is equal to 6.67 times 10 to the negative 34, and that is going to be joules seconds, and I'm going to multiply that by 3 times 10 to the 8 meters per second. And we're going to divide that all by my energy, which is 2.04 times 10 to the negative 18 joules. Now, when we do this here, we do our calculations, I'm going to end up getting 9.81 times 10 to the negative 8 meters is going to be my wavelength. So for this example, we have a table of energy levels for a mercury atom. Now it asks us what frequency of electromagnetic radiation is required to excite mercury atoms from the W to the Z energy level. So if I look at that here, we want to go my energy level from W, and we want to figure out, and we want to go from the energy level of Z. And we want to know what is my frequency for this. So I have to figure out which change of energy we have. So from W to Z, we're going to have 10.4 electron volts, and I'm going to subtract 1.6 electron volts. Because here is my W, and here is my Z. That's going to end up giving me 8.8 electron volts. Now, I want to change this to joules from when I do my calculation, so I have to multiply it by 1.6 times 10 to the negative 19 joules per electron volts. And this is going to end up giving me 1.41. So now we want to figure out the work energy. So my work energy, so my energy of my work, is going to be equal to Planck's constant multiplied by the frequency. Now we have to rearrange this for frequency. Frequency is equal to the energy of the work divided by my Planck's constant. Now we're going to substitute everything in, so I end up getting 1 point, which will end up giving me, once I calculate this, a total of 2.1 times 10 to the 15. And that is arc seconds. So which ones of these is that? This is going to match with A, so my answer is going to be A. In this example, we want to find the energy of an excited hydrogen atom when its electron is in the 7th Bohr energy level. So once again, we're just going to go here. My energy level of the 7th is equal to my energy level of the 1st divided by my number of levels that we want squared. So that is my energy level 7th is equal to negative, and it's hydrogen, so we know that's 13.6, divided by, and we're going to have 7 squared, which is going to end up giving me, if I look at this, obviously D, because 13.6 divided by 49 is going to give us the closest to D. My second last example is asking us how many different frequencies of light can be given off for an electron jumping from the 4th Bohr orbit to the 1st orbit. So we're looking at this here, and we're going from the 4th Bohr orbit all the way to the 1st. So there's 1. We could do that. Then it could maybe go not quite all the way to there, and then jump down here. So there's 2, 3. So I have 1, 2, 3. Then maybe he only goes to this one. This is 4. And then he could go to here, which is 5. And we already have this one, which is 6. So altogether, I look at this, I have 1, 2, 3, 4. And we have one more though. He could also go from there straight down for 6. So altogether, there are 6 wavelengths that can be given off. In our last example of this video, we have a computer monitor that displays the relative intensities of 2 emission lines of the helium spectrum. This here is the graph that the computer monitor shows. Now if I look at this, I have 2 different wavelengths. And my question is asking is the difference in energy associated with the photons from the 2 of the helium spectrum. So we want to know my difference in energy. That's going to be equal to Planck's constant multiplied by the speed of light divided by the wavelength, and we want to subtract Planck's constant multiplied by the speed of light divided by my wavelength of the second one. So here's 1, here's 2. For 1, we're going to end up getting 3.888 times 10 to the negative 9 meters. For 2, we are with
5.876 times 10 to the negative 9 meters. Now we must plug in what we know. So first is Planck's constant, which is 6.63 times 10 to the negative 34, and that's joules seconds. And we want to multiply that by the speed of light, which is 3 times 10 to the 8, and that is meters per second. And all of this is going to be divided by 3.88 times 10 to the negative 9 meters. And we're going to subtract this by Planck's constant again. We're going to multiply that by the speed of light, and we're going to divide all that by my wavelength. So when I calculate all of these, my units are going to cancel off nicely, so I'm going to be left with just joules. If we look at these, seconds cancel with seconds, meters with meters, so we're going to be left with just joules, and I'm going to end up getting 1.73 times 10 to the negative 19 joules, which is B. So those were some diploma-style questions that involve Bohr's atom.